A dark ribbon tightens beneath South Africa's winter waves, and the sea suddenly erupts. Thousands of sardines turn together as dolphins strike from below, and gannets fall from above. The spectacle is called the Sardine Run, although its scale changes dramatically between years. It is not a single orderly parade, but shifting shoals moving through a dangerous coastal corridor. Each fish gains protection within the crowd, yet the crowd becomes visible to hunters. The mystery begins with movement. Why do sardines enter waters where predators can concentrate around them? Cold water along the eastern coast appears to open a temporary route northward, but temperature, currents, food, reproduction, and population size interact in ways still under study. If you watched only the boiling surface, predation would seem to explain the entire event. Below that violence lies a larger investigation into oceanography and collective behavior. The sardines respond to neighbors within fractions of a second, compressing and expanding like living weather. Predators read those changes, testing the school for edges, gaps, and exhausted individuals. Every attack modifies the formation that the next hunter encounters. The run, therefore, becomes a moving contest between coordinated defense and coordinated pursuit. Its outcome depends on water conditions before the first fin breaks the surface. The principal fish involved is the southern African sardine, Sardinops sagax. Large stocks normally occupy productive waters along South Africa's southern and western coasts. During some austral winters, shoals appear along the warmer east coast in remarkable abundance. The inshore movement often follows a tongue of cooler water extending northward. Sardines generally favor cooler conditions than those dominating farther offshore in the Agulhas current. That warm, fast current flows southward along the continental margin, opposing the apparent northward movement. Cool nearshore water can create a narrow corridor between the coast and warmer offshore flow. When that corridor is weak or broken, the visible run may be limited or absent. This relationship is observed repeatedly, though it does not identify one exclusive migration trigger. Some researchers interpret the movement as a seasonal range extension connected with favorable temperatures. Others have examined links to spawning, feeding, and the unusual boundary between water masses. Evidence does not support describing every shoal as a purposeful march toward one fixed destination. Fish may advance, pause, disperse, or become trapped as local conditions change. Direct observations reveal sardine distribution, while measured water conditions define the corridor around them. Acoustic surveys can estimate fish layers below the surface, beyond the reach of human vision. These methods show that spectacular bait balls represent only brief fragments of broader movement. The predators also arrive through different routes and for different reasons. Common dolphins, Delphinus delphis, often form large groups around dense sardine schools. Cape gannets, Morus capensis, search from the air and plunge into accessible shoals. Several shark species join feeding aggregations, while Cape fur seals pursue fish near the surface. Bride's whales can engulf concentrated prey with rapid lunges through the school. These hunters do not create the migration, but their actions transform scattered fish into visible crises. Their presence is verified directly, while claims of perfectly planned cooperation require closer testing. The first pressure often comes from dolphins accelerating beneath or beside a school. They turn toward the fish, and the sardines tighten because proximity reduces each individual's exposed risk. That defensive cue produces a bait ball, a compact shape that predators can repeatedly attack. Dolphins circle, rush, and take fish from the margins as the ball loses room to escape. You can see coordination in their positions without assuming every movement follows a shared plan. Some attacks may be cooperative, while others are individuals exploiting the same concentrated resource. Sharks approach through the dense school, opening brief lanes before the fish close behind them. Their cue is a packed prey field. Their action is a rapid strike, and the consequence is renewed compression. Cape fur seals twist through gaps, using maneuverability to isolate fish separated from neighbors. Above, gannets detect surface disturbance and the dark shape of sardines within diving range. They fold their wings, enter the water at speed, and pursue prey beneath the surface. Their impacts further fragment the upper school and expose new edges to waiting hunters. The birds possess reinforced skull and neck structures and air spaces that help absorb diving forces. Those adaptations permit repeated plunge dives, but depth and prey position still limit access. Bride's whales exploit a different scale by accelerating toward a dense aggregation with expanded throat pleats. The cue is concentrated prey, the action is engulfment, and the consequence is removal of many fish at once. Whales must then filter water through baleen, making a compact school more profitable than scattered prey. Predator diversity does not mean every species feeds simultaneously at every bait ball. Weather, water clarity, depth, and school size change which tactics are possible. Aerial images can exaggerate order because one frozen moment hides failed approaches and shifting roles. Underwater sound may indicate dolphin activity, but sound alone cannot prove a specific cooperative strategy. Likewise, a dramatic surface boil cannot reveal how long the school traveled beforehand. Predators may follow sardines regionally, or they may gather after detecting local feeding opportunities. Their numbers can reflect both migration and rapid communication through visible disturbance. The safest interpretation begins with documented movement and adds strategy only where repeated behavior supports it. Even then, the bait ball is temporary, often dissolving when fish escape downward or predators lose contact. The run transfers energy from small plankton-feeding fish into many larger marine animals. Sardines consume plankton and package dispersed production into bodies predators can capture efficiently. When shoals enter coastal waters, that energy becomes temporarily concentrated near seabirds, mammals, sharks, and people. Cape gannets depend on accessible fish populations beyond the celebrated weeks of the run. Their plunging success links breeding condition to prey depth, distribution, and availability. Dolphins gain intense feeding opportunities, but they also spend energy searching across a variable coastline. Sharks encounter abundant prey without becoming indiscriminate machines. Their attacks remain shaped by opportunity. For you, the spectacle may look limitless, although the underlying sardine stock is finite. Fishing communities have long harvested sardines and other small pelagic fish for food and livelihoods. Management must consider population surveys rather than judging abundance from one crowded day near shore. A large bait ball can contain many fish while representing a small fraction of regional stock. Conversely, an unimpressive surface season does not prove the sardines have disappeared everywhere. Changing ocean temperatures could alter the cool corridor and the timing of coastal appearances. Shifts in the Agulhas system may change where fish, predators, and fisheries overlap. Predators adapted to recurring pulses may face longer searches when the corridor fragments. Human vessels also gather around feeding events, adding noise and collision risks at close range. Responsible observation requires distance because crowding can interrupt hunting and split animal groups. The ecological value of the run lies in its connection among climate, schooling, and predation. It reveals how a narrow temperature boundary can reorganize an entire visible food web. Yet the system remains variable enough that no annual spectacle is guaranteed. Future evidence must distinguish fish movement from changes in observer effort along the coast. Long-term acoustic surveys could measure offshore shoals that never form dramatic surface bait balls. Temperature and current models could test whether corridor continuity predicts northward distribution each winter. Tags small enough for sardines could clarify individual movement, though attachment remains technically difficult. Predator tracking could reveal whether dolphins, sharks, birds, and whales anticipate or merely encounter shoals. Stable records across quiet years are especially valuable because they test explanations without spectacular bias. You would learn more from comparing absence and abundance than from filming abundance alone. Future models should predict where cold water, fish density, and predator access overlap. They must allow separate shoals to respond differently instead of treating the run as one organism. Such benefits may be opportunistic and need not imply cooperation between species. Population monitoring will reveal whether changing appearances reflect stock size, distribution, or both. The strongest explanation will connect offshore conditions to each compressed school near the beach. It will also account for years when cold water appears, but sardines remain scarce. Until then, the run is a recurring possibility shaped by fish, currents, and hungry attention. At the surface, one final bait ball opens, scatters, and vanishes into winter water. The Sardine Run endures not as a guaranteed migration, but as a conditional convergence of ocean climate, collective defense, and predatory opportunity.